Hello again. In the last topic, we studied how the first derivative affects the shape of a graph. In this video, we are going to look at a new topic called concavity and how the second derivative and the concavity of a graph are connected. So let's look at these four curves. We have two curves that are increasing, but notice that they're increasing in different ways. Similarly, we have two curves that are decreasing, but again, notice they are decreasing in different ways. So if we were to look at the tangent lines for each of the graphs, so in other words, if I take some points on each of these graphs and draw some tangent lines. So for example, if I was to draw the tangent line at this, I was to think of the slope at that point, it might look like this, and there's the tangent line at this point. I'm just drawing some tangent lines. Notice how all of the tangent lines that I just drew are below the curve. Now let's contrast that with this second curve to the right, and I'm going to draw some tangent lines. Notice how those tangent lines are all above the curve. And again, if we look back at that first curve, it is increasing. But now look at the slopes. Look at the slopes. Look at the tangent lines. Think of those slopes. Are those slopes increasing or decreasing? The slopes are also increasing. So this curve is increasing at an increasing rate. The second curve is also increasing, but now look at the slopes. If we think of the values of those slopes are decreasing. This curve is increasing at a decreasing rate. Now let's look at these curves that are decreasing. And again, in this first example, if I were to draw a few tangent lines, those tangent lines are all below the curve. This curve is decreasing, but now look at the slopes. The slopes, if we think of the values of the slopes are going from more negative to less negatives. Those slopes, the values of the slopes are actually increasing. This curve is decreasing at an increasing rate. You know, that might sound strange, but it's decreasing at an increasing rate. And this last example, this last curve, is also decreasing. And if we were to draw some tangent lines and think about the slopes, notice how those slopes, some of them are poorly drawn, notice how those slopes are decreasing. This curve is decreasing at a decreasing rate. And so we have a couple things in common and a couple things that we can contrast. Notice how both of these, the two curves on the left, the tangent lines were below the curves, and both were either increasing or decreasing at an increasing rate. The examples toward the right, the tangent lines were drawn above the curve, and they were either increasing or decreasing at a decreasing rate. And this leads to the concept of concavity. These curves on the left are both what we say are concave up. These curves are concave up. The curves that are to the right are both concave down. And so when we talk about concavity, it's actually, the concept actually has to do with how we would draw the tangent lines to the curve and how those tangent lines are relating to the curve and whether those slopes are themselves increasing or decreasing. But a simple way to sort of think about concavity is if you were to pour water on top of this, if you were to kind of pour water over the curve, would the curve hold the water over that portion of the curve, or would the water fall off, right? Water's held, right? This would hold the water. And this piece, the water would fall off. All right, and sort of think about that for this curve. If I was to pour water on this part of the curve, it would fall off. And if I was to pour water on this part of the curve, it would sort of be held. So that's a less sophisticated way to think of concavity. So here's some definitions. A function is concave up on an interval if the graph of the function is above the tangent lines to the graph on that interval. And that's how I explained it in the previous slide. Similarly, a function is concave down on an interval if the graph of the function is below the tangent lines to the graph on the interval. Again, that's how I explained it in the previous slide. So that's what we really mean about concavity. Now, there are places in a curve where the concavity can change. We call those, if the points are defined for the curve, we call those inflection points. A point x equals c is called an inflection point if the function is continuous at c and the concavity changes at that point. So, for example, if we look at this curve on the left, notice how the curve is continuous. And if we were to sort of draw the tangent lines over that portion, the tangent lines are all above the curve. And so here it's concave up. And then it switches. Now, if we were to draw the tangent lines, they would all be below the graph of the curve. Here it's concave down. And so there's a point in here. This is an inflection point. Again, this curve over here, there appears to be an inflection point. Oh, right about there maybe. Somewhere in there, there's an inflection point. Okay, so notice if we sort of break up the curve over this interval to the left of that inflection point, here the curve is concave down. And then to the right of that inflection point, the curve is concave up. All right, so if the function is continuous at that point C and the concavity changes at that point, either from concave up to down or concave down to up, we call that an inflection point for the curve. So here's a graph from the Paul's online notes. A graph of a function is given. Determine the intervals on which the function is concave up and concave down. State any inflection points. All right, so we're not talking about increasing and decreasing. We're simply looking at the curve and trying to determine where is it concave up, where is it concave down, where does it change concavity, where are there inflection points. All right, so we're looking for points where the tangent lines, if we were to draw the tangent lines, would change from being above the curve to below the curve or vice versa. And so it looks like there's a point somewhere in here, maybe near about x equals -4. Notice if I was to draw tangent lines to the curve, they would be above, to the left of that, and then now they'd be below. The tangent lines would be below. All right, and then continues below, 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 and then it appears to switch again at -1. Now my tangent lines are all above. Oh, it switches again. Looks like it switches around 1, and then it's all the tangent lines are below the curve the rest of the way. So here's what it looks like to me. It looks like this curve is concave. Let's see, where are the changes? It changes at -4, at -1, and at 1. So over this first interval, it's concave down. over the second interval, it's now concave up. The third interval, concave down. And the last interval, from what we can see, concave up. So this is concave up on the intervals -4 to -1, or 1 to infinity. It's concave down on the intervals -infinity to -4, or -1 to 1. And we would expect inflection points. Well, not expect. We can see that there are inflection points. There are inflection points when x equals -4, x equals -1, x equals 1. And that's all we can say for that. We can't complete the ordered pairs because they didn't give us any scale on the y-axis. All right, so I don't know what this y value is. I can't tell. There was no scale given. So all I can say is that there are inflection points at those 3 x values. Now, if we were given either the y scale or if we were given the actual function that defines this curve, we could then calculate the actual ordered pairs for the inflection points by running those x values through the function. So it turns out that if we are given, instead of a graph to work with, if we were just given the actual function to work with, the symbolic form of the function, it turns out it's not extremely difficult to find the concavity of the curve and the inflection points. It turns out that they are related to the second derivative. And if we think back to how I introduced this, if we go back to the first slide, if we think about what I was saying, I was drawing these tangent lines, and I said something to the effect of, this line is increasing at an increasing rate. So that means, at an increasing rate, that means the rate of change of the first derivative is positive. Well, the rate of change of the first derivative, that's the second derivative. I said for this curve that this function is increasing at a decreasing rate. So that means that the derivative of the first derivative is negative. The second derivative is negative. And in fact, that's what we call the concavity test. Given a function, if the second derivative is positive for all x on an interval, then the function is concave up on the interval. If the second derivative is negative on an interval, the function is concave down on the interval. Inflection points can occur where the function is continuous and the second derivative is 0, or the second derivative is undefined. So this is sort of similar to how we figured out critical numbers and increasing and decreasing intervals and relative maximums and minimums using the first derivative, but now for concavity we use the second derivative instead of the first derivative. Similar process, different derivative. All right, so now here's another problem from Paul's notes. Here we are told the graph of the second derivative is given, so we've got to be very careful. This is the graph of the second derivative of a function. From this graph, determine the intervals on which the function is concave up and concave down. All right, so remember, for concave up, that means that the second derivative is positive. Concave down means that the second derivative is negative on an interval. All right, so let's see. Where's concave up? The second derivative is positive. Now remember, this is the graph of the second derivative. So all we need to do is find where the second derivative, where this graph is positive. This graph is positive over that piece and the second piece. So where is the graph concave up? Sorry, not the graph. This is the graph of the second derivative of the function. It's positive on those intervals I just highlighted in blue, which means then that f of x is concave up on the intervals negative infinity to negative 3, and then or 1 to 5. Where is the function concave down? Where is the second derivative negative? Again, this is the graph of the second derivative. So we literally just need to find where this graph is below the x-axis. And I'm highlighting those in magenta. So that means then that the function, the original function f of x, is concave down on negative 3 to 1 or 5 to infinity. We've got to be careful, right? This was the graph of the second derivative, not the original function. So we've got to make sure and read carefully what's given before trying the exercise. All right, so if we're given a function, if the second derivative is positive, the function's concave up. If the second derivative is negative, function's concave down. Inflection points occur where the function is continuous and the second derivative is 0 or undefined. Let's see how we can use those ideas with some actual functions. We'll start with an easy one. Nice polynomial function. All right, so we're given the function x to the 4th minus 6x squared. We are asked to determine intervals where the function is concave up, where the function is concave down, and any inflection points as ordered pairs. All right, so first, to answer any of these parts, we should always think about the continuity of the function first and the domain. So this is a polynomial. It's continuous over all reals, right? So this is continuous over all reals. So that's, maybe that's a step 0 for these types of exercises. We always want to think about the function's domain and where is it continuous. All right, let's calculate the second derivative. All right, well, the first derivative is then 4x cubed minus 12x, which means that the second derivative is 12x squared minus 12. Now, this function, this second derivative is never undefined, right? Because it's a polynomial as well. It's defined everywhere. So let's now solve. 12x squared minus 12 is 0. We add 12, divide by 12, x squared is 1, which means then the x is positive or negative root 1. X is positive or negative 1. So now, we run, like we did for our first derivative test for increasing and decreasing, we run something similar for the second derivative. We have important numbers at negative 1 and positive 1. I set up a number line. I put those important numbers. Here's negative 1. Here's positive 1. But now I'm testing into the second derivative. All right, so testing, how about negative 2? F double prime at negative 2, that would be 12x squared minus 12. And let's see, that would be 12 times 4. That is 48. 48 minus 12 is 36. This is positive. Again, I don't really care about the number. All I care about is the sign. Positive. All right, then I test f double prime in the second interval. How about at 0? f double prime at 0 would be negative. And finally, how about it at 2? F double prime at 2. And that will also be positive. All right, so what do we know? We have concave up. F is concave up on where the second derivative is positive. Negative infinity to negative 1 or 1 to infinity. Concave down on negative 1 to 1. What else do we know? The function has inflection points where the concavity changes and the function is continuous. It's a polynomial function. It's continuous everywhere. So I expect inflection points at negative 1 and at positive 1. The function has inflection points at negative 1, f of negative 1. I go back to the original function, remember, to find the actual point on the curve. So this would then be negative 1, and then substituting negative 1 into the function. Negative 1 to the fourth is 1. Negative 1 squared is 1, so that would be 1 minus 6. Negative 1, negative 5. And at 1, f of 1, which would be 1, negative 5. So the curve is concave up on negative infinity to negative 1, or 1 to infinity, concave down on negative 1 to 1, and has inflection points at negative 1, negative 5, and 1, negative 5. Let's see another example. Given the function f of theta is 2 sine theta plus sine square theta on the interval 0 to 2 pi, let's do the same exercise. So this one's a little tougher. It does involve some trig functions, but this would be a good idea for you to pause and practice this one on your own. I hope you pause to try this one out on your own. All right, so this is continuous everywhere. So it is continuous on the given interval 0 to 2 pi. That's what we'll focus on. Let's calculate the derivative. F prime at theta would be 2 cosine theta plus 2 sine theta cosine theta. Don't forget the chain rule on that term. And then we need the second derivative. F double prime at theta would be negative 2 sine theta plus 2. Now let's see, that would give us a sine f prime. That would be a cosine theta times cosine theta plus sine theta times negative sine theta using the product rule here. So I have negative 2 sine theta plus 2 cosine square theta minus 2 sine square theta. And I've got to find the important numbers. I've got to set this equal to 0. It's never undefined. I've got to set this equal to 0. Now, how do I solve this equation? It's got sines and cosines, and it's got sine squares and cosine squares. One technique would be to get everything in terms of one function. So I will use a Pythagorean identity to replace the cosine square theta with its equivalent in terms of the sine function. So then this becomes negative 2 sine theta plus 2 times 1 minus sine square theta minus 2 sine square theta is 0. Alright, so then this simplifies as negative 4 sine square theta minus 2 sine theta plus 2 is 0. So let's see, that would be then negative 2 times 2 sine squared theta plus 2 sine, plus just sine theta minus 1 is 0. And I think that'll factor. Negative 2, let's see, let's put it 2 sine theta here and a sine theta here. And if we put a plus 1 here and a minus 1 here, let's see, 2 sine theta times sine theta, there's the 2 sine squared theta, the outers. 2 sine theta times 1, that's 2 sine theta minus sine theta, that works, minus 1. That is the factored form. So then that means that sine theta, setting each of the factors to 0, sine theta is 1/2, or sine theta is negative 1. So then my important numbers on the interval 0 to 2 pi, all right, so on 0 to 2 pi, where is sine 1/2? So theta is, let's see, so if sine theta is 1/2, then on 0 to 2 pi, then theta is pi over 6, or 5 pi over 6. If theta is, or sine theta is negative 1, that means then that theta is 3 pi over 2. So we have 3 important numbers on our number line, and we're only considering over 0 to 2 pi. So here's my restricted number line. There's 0, and there's 2 pi, and here's pi over 6, and 5 pi over 6, and 3 pi over 2. All right, and I will use the form that f double prime theta is that nice factored form of negative 2 times 2 sine theta minus 1 times sine theta plus 1. Use that nice factored form to do my, to figure out the positives and negatives here on my sign chart. All right, so let's test. Now we can test the endpoints. We can test 0. Let's see, so what's f double prime at 0? Well, that would be a negative 2, which is negative. Sine of 0 is 0. So I have negative times a negative. Sine of 0 is 0 plus 1 is a positive. And so that would be a positive. And then how about a number between pi over 6 and 5 pi over 6? Let's use pi over 2. The sine of pi over 2 is 1. So then that would be a negative times sine of theta would be 1. 2 minus 1 is positive. Sine of theta is 1 plus 1 is positive. And that ends up being a negative. Between 5 pi over 6 and 3 pi over 2, how about, oh, and that 3 pi over 2 should be further over to the right. That's not very representative of the curve. 3 pi over 2 is, I don't know, maybe about here. All right, so how about we use pi? F double prime at pi would be negative 2, which is negative. The sine of pi is again 0. So we'd have 0 minus 1 is negative. 0 plus 1 is positive. So again, that would go to a positive. And finally, between 3 pi, and we can actually just use 2 pi. And again, the sine of 2 pi is 0. So f double prime at 2 pi would then be negative times a positive, which would again be a positive. So positive, negative, positive, positive. All right, so what is this telling us? The function is f of theta is concave up on 0 to pi over 6, and then it's concave up. Now it's not concave up at 3 pi over 2, so we can't include that point. At 3 pi over 2, the concavity is neither up nor down. So it's concave up on 0 to pi over 6, and then again on 5 pi over 6 to 3 pi over 2, and then again on 3 pi over 2 to 2 pi. It's concave down on pi over 6 to 5 pi over 6. And we see two inflection points. We have inflection points. Let's see, at pi over 6, and then at f of pi over 6, that would be 2 sine of pi over 6 plus sine square of pi over 6. Let's do a little side work here. Running out of room. Sine of pi over 6 is 1/2. So I'd have 2 times 1/2 plus 1/2 squared. So that's 1 plus 1/4. That would be 5/4. And at 5 pi over 6. 5 pi over 6. The sine of 5 pi over 6 is again 1/2. So again, we'd have 5 pi over 6, 5/4. All right, so that one was a little bit tougher because it involved a trig function. And sometimes they're just a little bit more difficult to solve the equations to find those important numbers. All right, so I'm going to stop this video, and we'll do a couple more exercises related to the second derivative, and we'll also introduce the second derivative test and show how we can use that to find relative maximums and minimums. All right, I'll see you there.